Oftentimes, parallel programming proves to be so challenging that we neglect a central endeavor in developing proper HPC code, and that is performance analysis. Very active and rich research area, performance analysis provides mathematical tools, methodologies, and mathematical model methodologies and tools for evaluating a computer code and identifying bottlenecks and inefficiencies. Our first speaker of the day has more than 37 years building state-of-the-art tools for understanding what is making your code run slow. Bernd Mohr is the division head for application support at Jülich Supercomputing Center in Germany, where he has worked since 1996. He is the lead developer of well-known tools like Tau and Scalaska and some others. He's the author of dozens of high-impact papers, a distinguished member of European projects in HPC. He was the first non-American general chair of the Supercomputing Conference in 2017, and a great researcher, mentor, and colleague. Please join me in welcoming the person who has done a wonderful job in building tools to show how awful your parallel code can get.
Buenos dias. Unfortunately, there's only things I can say in Spanish. I know a few more words, but not enough to give a talk in Spanish. So thanks very much for inviting me to this conference, and thank you very much, Esteban, to setting the stage. Why I talk about performance? I mean, we heard that already in the morning all the time. Yeah, we are proud ourselves to work in high-performance computing, HPC. Yeah, you could also say we work cluster computing or parallel computing, but that just would mean we use multiple processing elements at once. But HPC means we use these resources in the most efficient way with the least resources. Yeah, so in HPC, there's 3 letters, HPC, what's in the middle? P. P is performance. Yeah, so this is why I like to talk about it, and I really like to talk about it. And this, I guess, they invited me because of that. And I want to remind you, like Carla says, it's the Latin America High Performance Computing Conference. It's not a cluster computing conference. Again, it's a high performance conference. Okay, so performance. Let's see how that would work. Perfect. Performance, so the talk is about performance analysis, but in parallel performance analysis can mean different things. So just to make it clear in the beginning, what I will talk about in the next 45 minutes is, so there could be 2 ways of looking at parallel performance analysis. More analytical way, you think about, like deriving models for performance and so on. But you can also do empirical. So you have like parallel applications, HPC applications, you run them and you measure basically how good or bad they are. So it's empirical. So that's basically what we're talking about. Again, also parallel could be like more loosely coupled grid distributed computing, but I'm really talking here about HPC tightly coupled, a set of nodes, clusters in one machine room. Yeah, and then also when people talk about performance, you could monitor the whole cluster and system, but I'm really talking about the monitoring of one application running, and just as I said, to make clear what I'm talking about here. Just like very quickly a few words, Jülich Supercomputing Center, where I'm coming from, it's part of the Forschungszentrum Jülich, which just translates in English to Research Center Jülich. For people who know, like a national laboratory in US, like Argonne or Oak Ridge, it's just the same thing, just in Germany. Yeah, it's about yeah, we have our own little city. The campus is about like 2 kilometers by 1.5 kilometers, 40 institutes. Actually, the number's wrong. We are over 6,800 people now. We work on all kind of fields from research technology, health, energy, atmosphere, climate, and so on. It's a really nice place to work. And then part of it is the Jülich Supercomputing Center. It started out being the computing center for the laboratory already in the 60s and 70s, so we were working on it for quite a long time. But then we have, meanwhile, acquired different roles. So we're working very closely with the nearby Aachen University. So there's a Jülich-Aachen Research Alliance, JARA. Then we are one of the 3 national highest performance computing centers. We don't even have high performance computing centers and highest performance computing centers. So we are one of the 3 highest performance computing centers, together with the Leibniz Rechenzentrum in Munich and the Stuttgart Center in Jülich is the 3rd. And we are also serving Europe. In the past it was PRAISE. You might have heard about that, and now we are part of Euro HPC. And if you're following the news, we are actually getting the first exascale level computer set up in Europe, in Jülich. And as we are talking, they are delivering hopefully some containers which contain the system. And so this system is supposed to be ready next year. Okay, I understand this is a very specific topic, and before going into the details, I thought I'd give you like a hopefully 5-minute introduction about the most important terms, so for people who are not so familiar with the topic, have it easier to follow the rest of the slides. Okay, so typically when we do a measurement of a parallel application, it's like an experiment. Yeah? You have to prepare it, which means we need to prepare to collect data about the performance of an application, and this preparation is called instrumentation. We take the code, and the nice thing is code is very malleable, so we just use different ways to inject extra code into your application, which collects extra data, which later allows us to assess the performance of your code. So that's called instrumentation. When basically you execute this instrumented application and you run it, and it does the normal job, does all your calculation, your weather simulation or bio calculation, but in addition, at the same time, spits out extra data, and that phase is called measurement. And after you're done, we have this set of extra performance data, we analyze it, and then there's typically some presentation component, like some graphics, user interface to allow you to look at the data, browse through it, and get hints about what's wrong in your application. And then the last step is, once you know what's bad in your application and where in the application, you need to like change it and improve it. And this portion is called tuning or optimization. This is the most complicated part, which is why we leave it to the user. But the reality is, how to fix the application, how to change the algorithm typically depends very much on the application area. And we, as performance expert, we are not experts in all these application areas. So this is why, at least together with you, we have to work on it. And the important part, this is a cycle. Yeah? So you measure, it's your bad, you fix it, and then sometimes people stop here, but no, you have to go back, do the same thing again, run it again, and see whether you actually fixed the problem. So you often fix the problem, but then the problem moved somewhere else, or you created a new problem. So you basically go through a cycle until you run out of time, or at least, like hopefully you get some reasonable level of performance, and then you get out of it. There's 2 dimensions when we kind of structure measurement. So the first dimension is, when do we do a measurement? And that the measurement of a specific data can be triggered either from the outside of a program, which is called sampling, basically. Yeah, like either the operating system or some hardware is interrupting your program at a regular interval, and every time it gets interrupted, you take a measurement point. That is nice because you don't actually have to change the program, yeah? Because all the necessary triggering comes from the outside. The other option is internal triggering. So what I just told, basically we use different methods to insert extra code into the application. And unfortunately, we never, in 20, 30 years, we never came up with a good word for this method. So it's code instrumentation, but it's not a word like sampling here. So that's one point. So either from the outside or from inside the program, like we interrupt the program and collect at that point some data. And now what do you do with the data? One way is to basically just sum it up, make a statistics about it. This is called profiling, or creating a profile. The other way is you write down a protocol was happening, yeah? Like that time, this processor did this, next time, so you get a protocol out, and it's much more detailed. So we're much more, this is called tracing. Tracing is much more powerful, but you can already imagine if I basically write down in a large parallel system, whatever processor is doing in every microsecond, this data can get very, very large very quickly. So typically what you need to do is basically start with a profile, because it's just independent how long the program is running, it's just statistics. It's adding up and there's a fixed amount of data. Okay, here's some more details about what I just said. Yeah, profiling, the advantage is it works for very long programming. The disadvantage is you lose what's happening over time. Yeah? Tracing is really powerful, allows you to reconstruct the dynamic behavior over time, at least on the level of the data you collected. And the funny thing is, because you have all the timing data in that trace, you can calculate the profile out of the tracing data in advance. So it's the most powerful technique, but the main disadvantage is that it's so much data, and I can't tell you how often my team killed some parallel file system in the past 30 years because we just generate too much data. Yeah, it's perhaps a little too complicated slide. So just giving the process of tracing, so you start with two processes, and then have a function foo on one processor, a function bar on the other. Then you send a message with some communication library from one to the other, and these blue lines in there is basically showing the instrumentation. You collect that with some external clock. You do that, and then you get these trace files, as I said, on every process, which record the time, what's happened, additional parameters, and some tables. And then you merge them together, and you get this global view, which we call the global trace. How is that useful? And many tools do that. Looking at these trace files, I mean, is not very interesting, but you can generate so-called timeline visualizations out of it. And it basically works like that. You have a line for every processing element or for every core or every node, and the color indicates what it's doing over time, and then with arrows and other things you can show messages or synchronizations and so on. And this way you quickly can see what's going on dynamically. And yeah, because you expect typically that every process doing the same, so you should see columns of the same color over time. And if it's not fitting, you quickly can see something is going wrong. So that's basically very quickly an introduction to that. Unfortunately, it looks like you loaded the PDF and not my PowerPoint. You had some nice animations to make it easier to explain, but okay, let's see how to cope with that. So why do we do that? This is the reason. Yeah, so I had it easy when I started years ago. It was single core processors, and when you had a bunch of them connected by a network, and there was at some time, we invented MPI, so you had basically distributed programming, MPI. Every process had just one core. It was complicated at that time, going from just vector computers to that, but looking back after 30 years, it's simple. So what do we have now? So we have now, again, we have a collection of nodes. This is the green part. But in each node, we have multiple sockets. And so they are CPUs. In the modern machine now, thanks to AI and other things, we also have accelerators. And in a big node, you have multiple multi-core CPUs and multiple accelerators. Yeah, like Jupyter will have per node 4 72-core ARM Grace chips and then 4 H100s in one node. And when you look at these chips, as I said, they are, again, like many cores, multi-cores. Yeah, so the processors have many cores. When you look at a graphics card, again, it's basically lots of thread engines, again. So what we have is not a parallel system, but we have a parallel system composed out of parallel systems, composed out of parallel systems. This is how we are currently now. And it's not just the processing, it's also the memory. Yeah, you have memory on the node, you have memory in every processor, you have caches in the multi-core. Sometimes they are shared between two cores or like a group of cores, you have NUMA domains and so on. And parallel computing means you have to distribute the work of all these processors and you have to distribute the data to the memory. But it sounds simple, but yeah, like look at that picture. So where do I put which calculation and where do I put the data necessary for this computation so it's most efficient for the processor to make that going? Why do we have these architectures like now? I don't know. This would be a very good question for the special keynote after lunch from my good friend Matteo Valero. He's a computer architect. Perhaps he can tell you why we have such systems now, and hopefully he'd tell us a little bit about the future, how to make it simpler. So what does that mean? Yeah, and we have these HPC systems, they are very complex, they're heterogeneous, and what a lot of people don't realize, they think, okay, it's a computer, it's not changing, but it's a living machine. Yeah, so nodes fail over time. Depending on the load, they heat, like they get hot, and especially GPUs automatically slow down, like in the frequency, if they get too hot. So if you have an application and you know, oh, here's some hotspots, you could kind of think about, oh, like here, the GPU will heat up and will slow down my application. But it can be worse because the systems are so large that typically multiple applications of other users are running at the same time. So you could be in a bad luck that some parts of your code is running in a rack with a highly performant other guy, and he heats up the rack, and then suddenly parts of your some processes on some GPUs are slowing down because of someone else. So yeah, that's one thing. And then, so the hardware is like increasingly complex and dynamic. Secondly, yeah, because of its structure, like I said, when I started, it was just MPI. Now we have to know MPI to do the synchronization and messaging between the nodes. You have to use something like multi-threading, OpenMP or so, to use the cores. And then you have, unfortunately, currently a multitude of ways to program GPUs. CUDA, HIP, SYCL, Coco, Strata, OpenAPCC, yeah, you name it. And you have to put it together to make use of all that system. And you not only have a problem of making each of them work, but you also have a problem to making them work together for your application. So it's really fun. So what it basically means, yeah, like most people, especially like people new to the field, they get overwhelmed by that. And then, yeah, he said, I'm the head of division application support. So these people in my center come to me and say, help me. Yeah, like make my program fast. Yeah, I need to calculate the weather for tomorrow, but the calculation takes 1.5 days. So it's not very helpful. Okay, so this is where we come in. So you want, I mean, of course, what you do if you do, you develop software tools to help you analyze, like measure analyze and give you ideas into bottlenecks, what is wrong in your code and where, and potentially some idea to fix it. So there's, over the years, many people worked on it, many people developed tools, and I cannot talk about all of them. So what I did in this talk, I said, I want to say, these are things people want to have. The tool should be portable, yeah, because typically 1 year you work with that university, next year you get an account, another one, they have a different system. You don't want to learn a different tool just because. So the tool should be work everywhere. It just should give you numbers, but like it should give you insight into the code. You want to, over time, work on larger and larger systems and applications, so the tool should be able to scale up, also to very large run. It should integrate it, and you will learn very quickly what I talk about it. Ideally, it should be also maintained. Unfortunately, a lot of things get developed at universities as part of a PhD project. At the end of PhD project, you have something working. The PhD person leaves, and then 3 years later, it was a nice tool, but it's not working with the latest operating system version or the MPI version anymore. And then what I always hear, especially by my users, it should be easy to use. I perfectly understand. It's a reasonable request, but when you look back at my last 2 slides, I mean, the hardware is extremely complex. The software is extremely complex. So why should my performance tool be easy? Yeah, I would like to make it easy, but I tried for 30 years and we horribly failed. Yeah, the only thing we could try to do is make it as easy as possible, but it doesn't mean it's easy. Yeah, okay. So when you have this list, which tools out there you want to look at? And it's a small list. So very quickly, so there's the Tau tool from the University of Oregon, HPC Toolkit from Rice University, Extra-E and Paraware developed by Barcelona in Spain, Jesus Alberto and his team. And then people, me and other people in Germany, so there's Vampire, and then Skalaska and Scorpi. They basically, these belong together, and I explain a little bit more. There's also very nice vendor tools out there. Intel vTune, AMD, ROCm, Omnitracers, and whatever. Why they are not on the list? They are not portable. Yeah, so you can only use NVIDIA Nsight. Great tool, but it only works on NVIDIA GPUs. So if you don't want to learn to switch, you might want to look into these tools. And they are all, like most of them are older than 15 years and are still maintained by a large group of people. So the chance that they will be there another 10 years is quite high. This is why I recommend them here. Okay, so very quickly, portability. This is the tool I'm working on with my team is Kalaska. This is the list of systems we try to support. Yeah, and basically when it comes to clusters, it's Linux on every processor you can get your hands on, and then all these special machines like the Chinese Tihanya systems, the K computer, Fukaku. It worked on Blue Gene and all the Cray things, and there are probably some things missing here. Luckily, over time, it got simpler. Basically, all large supercomputers are using Linux now, not different versions of some commercial Unix. But still, even you say, I just have a cluster of Unix, it's because you want to support OpenMP, and OpenMP is part of a compiler, and every compiler does it a little bit differently. We need to basically take care of, oh, does it work with GNU, with Intel, PGI, Clang, IBM, Cray, Fujitsu, ARM, Clang, and whatever. The list is endless. And the same thing with MPI. Okay, so that's about portability, but you don't really have to take care of it. This is a challenge basically for the tool developers to really support all of that. So I think this is the interesting and more important part. So how can a tool be giving you insight and not just numbers? Okay. Another problem with slide, because PDFs, in the PowerPoint, I did hide some slides. So now, but in the PDF, there are all of them. So I go, about some slides I go very quickly, but I included them because perhaps after that you want to look at it. So Tau is a very portable tool, allows profiling, tracing, has all different instrumentation modes. I actually started it in '93. And I realized there's probably quite a few people in the room who haven't been born at that time yet. So it's worked on it a long time. And some people call it the Swiss Army knife of performance tools. But as I said, we work on 30 years on it, so it looks a little bit like this Swiss Army knife. Don't tell Samir, who's the currently developers. He doesn't like me showing that picture. HPC Toolkit. Rice University, John Malacramy. It's a sampling tool. The sampling tool means you can run it on every binary application without instrumentation, which is very useful. Yeah, and even if it includes whatever MKL or some commercial library where you don't have a source code, but it will try still to give you lots of insights. So it's a really nice tool. Extra eParaware is also like a timeline and an analysis tool, but it's programmable. It's very flexible, really nice tool. Vampire is, yeah, as I said, things we are working on. It gives you this, as I said, this timeline, measures hardware counters, and then you can analyze the, yeah, like you see what the code is doing and what is the whatever, like here, the total number of instructions. All the black lines are messages and so on, and then you can kind of zoom in and you get more details. And if you know what you're doing and you know what to look for, this tool is quite helpful. The problem with it is, yeah, like when people show you this tool, they show something on the left. So this is a measurement on an exercise program of an MPI class. You tell the students to send an MPI message around the ring. So processor 0 sends a message to 1, to 2, and so on, and you can nicely see it. So yeah, here, yeah, it's like, so here you see the message going through. In the beginning, everyone is waiting to receive to get his message, and once they are done, they can finalize. You can nicely see what's going on, but here on the right side, it's like a real-world example. So this is just 64 processes. All the black lines are messages, all the purple are collectives, and it's get a little bit more complicated to find what's going on. And now think about you're running on 2,000 or 100,000 cores. There's a limit to how these timeline tools, which are very intuitive, they're just not scalable. Yeah, they work fine in a node, or you have like 1 or 2 or 3, 4 GPUs, but if you go beyond a node, it's not so useful anymore. So, and then each of these tools, they not just have all these profile and timeline displays, but also they have a right mouse button, context menu, and you can configure all these diagrams. And so the typical user says, like, yeah, like a picture is worth, I forgot what is known as, what is the usual idiom? A picture is worth in 1,000 words. Yeah, but as I said, what's about thousands of pictures? It's typically just a big mess. So when we started about 20 years ago, we said, hey, we are the performance experts. Can we not just do it a little bit more automatically and help the user? So the idea was basically, okay, at that time it was MPI. We just define what are the typical performance problems when you work with MPI. And here's like a very simple application. Yeah, everyone is working. This is this yellow Velo card. And then the last process is done early. And he waits for a message on the top. But because the send comes so late, this portion of a receive you kind of waste. Yeah, and then this is called, we call it late center. And so what we basically do is we just sit down and we came up with a catalog of these performance problems. For each of the performance problems, we defined the structure, give it a name, and for each of the problems, we defined what portion you waste. Yeah, and then basically explained in 2 minutes what my tool does is it measures your code, gets all the data, and then does a search for these patterns, and at the end tells you, oh yeah, you had 10,000 of that problems, 5,000 of that problem, you wasted so and so much time on your code because of that problem. So I can rank the problems, and we tell you where in the code it is. That's basically what my tool does. Sounds simple. The problem is do it in parallel. Because you can do this search very nicely if you have everything in one processor, in one memory, but think how you want to do this search for these problems and the ranking in parallel. And this is basically what we worked on in 20 years, and this is kind of our success story. So here's some other examples. We cannot just do the simple late senders, but here's like a situation, like if there's a late sender, basically that's that portion, we look, was there another message sent earlier but to the same processor? So if I, like this guy, would have first waited for this message and then it would have been faster. So we call that late sender because of wrong order. So we have more and more complicated problems, and the more complicated we get, the more information we give back to you why something is wrong. Yeah? And then we have, as I said, like a long list for MPI, we have a performance problem for OpenMP, and so on. So this is this Kalaska tool. It allows you either to just do a scalable call path profiling, and then we also can do the trace analysis in a scalable way. And I'll show you later how far we get. Basically what we do is, I said, we get these traces, and then in parallel, so basically you run your program, and in the same job, you start at Kalaska Analyzer, and it uses the whole parallel system in parallel to do this bad situation trace, and at the end gives it out. And because we never try to visualize it in a timeline, we can go quite far. And I show you at the end how far we can get. So this is how the tool looks like. It's, I know, this is where the not so like easy to use things start, but roughly on the left side you have the different statistics and metrics we collect, like execution time, the number of the number of synchronization, number of communications. The number next to it says, yeah, like here, execution, it was 1.83 to the power of 5 seconds of execution time, and so on. And in order to quickly find you high numbers or bad numbers, we put the color there, and the more red it is, the more higher is the number. So you just look, oh, where's the red numbers, and then you easily find the problem. And like here, yeah, like it's hierarchical, so execution time can be user time, MPI or OpenMP. Inside MPI, it can be synchronization, communication, time. Inside communication can be point-to-point and collective, and you get deeper and deeper. And you can kind of select the level of detail you want to go. And then, like here, I said, okay, late sender is, I want to see the late sender, so I click on it. And then this is 1.74 to a power of 5 seconds. When I click on it, now in the next level, I see the call graph, and I see how the number of late sender seconds are distributed over the code. And again, I see all the places where late sender is happening. And in this nice case, of course, it's a real application. It's a community Earth system model, sea ice calculations from a climate calculation on over 4,000 processors. But it's a nice one, so I always use it in my talks. But you see here basically there's a weight all, most of the things happening is inside, calculation of the ice boundary, and so on. So we know there's a problem, yeah, like when we calculate on the boundaries of ice, there's a late sender problem, and again I can click on it, and then over all the nodes and processes I can see how this number is, like where is the bad things happening. Left? Okay. Okay. Yeah, and then very quickly, yeah, like the list is not very nicely, so if we have topology information, like of course here in the sea ice module, we work on a map of a world, and then you can see basically like each square is the processor handling that portion of the data, and then I can see like that overweighting is happening in an equator area, and it kind of makes sense because there's not much ice there, so the processor has not much to do. Yeah, and this is what I mean by insightfulness. It gives you information where you think, like what problem is happening, where, and it gives you also, ideally, it's not always working, some feedback about the application domain. This was the beginning. People complained, yeah, but the weighting is actually not the problem. The problem is actually some load imbalance which causes the problem. So where is the load imbalance? In many cases, it's just in front of that barrier or whatever, but it could be, it's also like a few phases earlier. So what we do is, like we search forward in time for these problems, and then we found the problems, we're going backward in the data again to find the source of a problem. Yeah, and this is kind of indicated here. And then when you do that for that sea ice problems, what you find out here, this is kind of the point I want to make over here is the developers thought, of course, is perhaps some load balancing problem that we are not distributing the hotter portions of Earth directly, but we found a bug in the code. When you look like on the reddish colors here, it's not so good to see, but it's basically the problem comes from complicated coastlines, like Japanese islands, Aleut Islands or something. It was a bug in the code there. And the load imbalance there triggered basically the rest of it. Yeah? This is a very ideal case. Like when you try our tool, it will not work this nice way, but we can get you close to it. Yeah. Okay. This was about insightfulness. Quickly about the other things, integration. You wanna sure that a tool ideally supports all level of parallelism. I said that already. Yeah. Internode, intranode, accelerators. It might be nice if it's integrated with modeling and prediction. And yeah, one tool is typically enough. You want to also make this interoperable. Yeah. Here I put together how the different tools I mentioned, what they are supporting. Of course, there's no official meaning what support means. Yeah, it could be they used the Hello World example, tried and said, oh yeah, now I'm supporting HIP. Or yeah, but this is basically from their websites what we're supporting. And you see on the list, the last 10 years it really got complicated because of all these multitude of GPU models. Yeah, before, like everyone supported MPR and OpenMP. Yeah, it was really nice, but now it's getting complicated. It's a lot of work to make this going. Here's just examples of the different tools, how we are supporting like whatever, CUDA, multiple things and so on. There's another thing of integration, which we were lucky to get funded in Germany, is all these different tools need to collect data, and all need to support like MPI, OpenMP, all the compilers. So all these people working on these tools do the same work as part of their work, which is kind of a waste. And so luckily about 15 years ago, the German government gave us some money so that the Vampire people, the Skalaska people, and the Tau people got money to basically make one measurement system which we can use when in all the tools, and when you have more time actually working on the tools, and this is called SCORP. Yeah, I don't have the details, and I said this is how all these tools are integrated. You get profiles and traces, and unfortunately I don't have the time to go into details here. Yeah, it was, as I said, it was not planned like this. The PowerPoint, I had much less PowerPoint. Quickly about scaling. Here is the data from the top 500. You probably all know top 500. It's a list which comes out twice a year. People run a specific benchmarks called HPL, measure how much flops they got out of it, and then this is basically like like for a horsepower for a car, it's like a number for your system, how good you are. And then we take the 500 systems with the highest numbers and put them on a list. And it's good for computer center people which can brag, oh, I'm in the top 10 or top 20. But the useful thing is, because we have that list for over 25 years now, you can see the trends on the systems. And one interesting one is, how did the number of cores in the system develop? So when you look at on the left side, I start with 2000. The largest system at that time had 10,000 cores, and the small 10. And it's logarithmic. So if I would a normal scale, it would go like this. Now, the largest system officially on the list has 10 million cores. The smallest system has a little bit, like roughly 2,000. In many ways, this Chinese system with 42 million cores, but Chinese decided not to publish their numbers in the top 500 list. But what I want to show here is, if you say, I want to work on a reasonable size of high-performance computing, I mean, you don't want to say, like, top 20 systems are a little different, but even the average system has now around 300, like 200 to 300,000 cores. So if you say, my application, my framework supports the average top 500 computers, you better support running on 200 to 300,000 cores. In order to make the parallel tools working on it, we have to basically also do it in parallel. Like all the data collections in parallel, reduction is parallel. These systems are built for very powerful parallel computation in working on lots of data. And so it's actually not a problem to collect a lot of data, unless you kill the file system, but you can use the power of that system. If you, I collect the data and then I use my laptop to analyze the data, it's a bad thing. Like if you want to really do that, you also need to use the full computer to do that. And here is some experience, basically how good the tools are in that respect. So I have two columns. The first column is the largest reported run by the tool developer, so they know their tools best. And then the right side is like, if you are a trained user outside the developer team, what do you expect? And you see the numbers. So most of these tools, extra paraware, they still use a global trace file. So like they have a kind of limitation not to go beyond like 1,000 or 2,000. But the others, you can easily analyze 10 to 100,000 of cores. So what I wanted to show actually was, let's see. This slide, which I'm proud of. So this is the largest test case we ever got our Scalaska trace analyzer to work on 1.8 million threads. It was basically on a uQueen, which had 28,000 cores with 64 cores each. So this is you convert, and it still works. You still see, there's a problem in the critical OpenMP, and you see exactly the critical region is inside that code. And there's no way to show like 1.8 million cores, so we give you statistics of a distribution and so on. And as far as I know, I don't know what NSA is doing or the US weapons lab, but for me, this is the unofficial world record of the largest tool execution so far. So the interesting one is, and I think this is, I want to close with that 2 slides. Is that fine? So this basically gives you a very quick overview what tools are out there, what can they do, roughly what kind of information do you get. And of course, in order to be able to use them, you have to use a training or something, and you cannot learn it here in half an hour. But basically, what's not working? I mean, we're working on these tools for 30 years. What is still not easy with these tools? So the first one is, which you think, it's very useful, but the tools are not very good in it, is giving you feedback on your memory usage and vectorization. Why is that so hard? Because we collect most of our data on the software level. And these things, like memory access and vectorization, is done in the hardware level. And you have a hard time getting access to what's going down there. There is these hardware performance counters, some people know. The problem is every processor, not every, like say, not just like Intel or something, every processor, how you call that, version or something, has like slightly different hardware counters, slightly different meanings. So it's, and then they have always, it's like different meanings. And so in order to, for my tool to give you the same interesting, nice insight into vectorization, I would need to know how all these processes are working, find the necessary hardware counters and how to analyze them to program that. And as an open source developer, I cannot just handle that. So the vendor tools are much better in here, like ViewTune and others, but of course they only work for their processors. And especially with GPUs, but also outside, we see a trend to a based asynchronous programming model. So before that, yeah, you had everyone is doing the same. You synchronize or broadcast and send messages, and also the early versions of OpenMP, you just did like this parallel loop synchronize, parallel loop synchronize. It was very synchronous. Everyone, and when looking for performance problems was easy, yeah, you looked at timelines or statistics, everyone should do the same, and if it was not the same, there was a balance problem. Now, yeah, it's more like executing kernels in parallel or tasks. And what I told you earlier is systems are dynamic. So it could be by either your program, but also the whatever room temperature, the phase of the moon, whatever, the mood of a system administrator. Could be that your task execution goes a little bit differently, and every time you run it, you get a slightly different result, which is a problem for me. So like I told you, what we do is we make a measurement, look at the data, based on that, we optimize it, run it again, and see it's better. But if there's already a change, if I run it multiple times, how can I decide if I did the optimization when it works better or worse? Did it come from my optimization try or just because the tool itself? Yeah, like just had a bad moment and so on. So it's getting harder and harder to make this work. Then, yeah, I started, yeah, with Fortran, of course, in C, yeah, and then people started C++, okay. Now Python, Ruby, whatever, Rust, Julia. So it's getting harder and harder, and especially like things like Python. I mean, it's great, and there's great packages to allow you to do really even efficient high-performance codes with Python, NumPy, lots of stuff, yeah? But the problem is there's interpreted, and when I measure, I collect more of the data on the run level, and I have a harder time giving you insight on your interpreter level, yeah? That's a problem. And then, so far, I told you we basically look at what is a specific application doing, but that's now no longer the usual way of using a supercomputer. You typically have a whole analysis workflow. Yeah, some preparation, running a whole series of simulations, and post-processing, putting the data together. And you need, yeah, I mean, of course, I can use my tools to look at each of a step, but it's the thing missing to put everything together. Yeah, and then I think AI is great, and it will solve a lot of things in the world, but yeah, I'm getting close to the end of my career, so I decided not to start on working on AI or performance analysis, but I invite you. It's an interesting field. So basically what that list is, like this page and that one, if you're looking for some interesting way to help society, this is the way to go. I mean, you can work on bioinformatics and genome and whatever, but you have to see it this way. You help society in one specific area. if you work on tools, these tools help all the other scientists to get their results faster or doing higher resolution. So you help everyone. So I know it's not as sexy as like the big things, but this is why I really like to work in that area, and I work on it for 37 years. And so basically, with that, I want to close. In the slides, you find pointers to videos with background information on this how to use the tools. I found some blog articles summarizing tools. There's a great website, VIHPS. It's a collection of tool developers, and they every half year we bring out a tools guide, which is like a collection of all the tools they know about and so on. So this is useful resources, and with that, I want to close, and I more or less, I hopefully in time, and hope I didn't bore you to death. And I'm here all week, so even if you don't have time for a lot of questions, I'm here all week, and just talk to me. You notice I really love to talk about performance, so and I'm happy to talk more to you about performance beyond this keynote. Thank you very much.
All right. Okay, we have time for maybe 1 or 2 questions in the back. I guess the microphone will.
Yeah, okay. The question is about the importance of checkpointing. Yes. This is not, the thing is, because the systems are so complex, the longer the program runs, the higher the chance that something goes wrong. And the main problem is, especially all large programs use MPI, and in the way current MPI is working, if one node fails, it takes down the whole system. So what a typical compute center does, it puts limits on the queue how long we can run a program. In Germany, we typically use 24 hours. A lot of people are angry about that because they run for like 3 days, 5 days a week, and it forces them to introduce checkpointing. So that basically after 23 hours, they checkpoint, and then the next day, the second job continues with that. They said everyone doesn't like it, but everyone at some point runs into a problem, the computer goes down, they lose the calculation, and then they are extremely happy that they didn't lose all the calculation, but only the last 23 hours. So, yeah. Everyone needs, like, if you're running longer, introduce checkpointing in your program. It will really help you in the long run. I hope it answers the direction you were thinking of. Yeah, yeah.
Okay, so just one more question here in the front.
Okay, so how do you see the challenge to measure the data? How do you see the challenge to measure the data movement between the CPU to cache, and even the cache inside of the CPU, the GPU as well, and also through the network, with different GPUs connecting to each other? It's the same challenging of vectorization using hardware counters?
No, it's not as bad. Yeah. So currently, like typically this memory movement is left to the user. So there's typically like for CUDA, there's a CUDA memcopy in and out. So I can capture that routine, measure the time, and like for the message, I can say, oh, like you're waiting for that data, but it took too long, so I can do the analysis. But of course, we want to make it easy for the user, so more and more we have this unified memory and memory spaces, and more stuff is happening again then on the hardware. And then we get, as you said, into the same problems. How do we get information? The different GPU program models have different levels of tool support. I cannot go into details here. Some of them give me this information, some not, and But we work very closely with all the vendors on that. The nice thing is, as we are around for 20, 30 years, when we come say help support us, they're typically very open and help us. So, like my developers, we have like bi-weekly meetings with the AMD support team, because we currently try to support Ribbon and Hawk, and the same thing with Intel. Intel even paid us a person for a while and stuff like that. So yeah, but you're right. It's the more we try to make it easy and move it into hardware, the harder it is for the performance analysis tools to capture information about it. Yeah.
All right, let's thank the speaker again. And before we move on to the next activity, which is a panel, we would like to give Bernd a present from the organization.
Thank you so much.
¿Que quieren pasar un aviso por un problema en la mochila? ¿Me ayudas con eso? Sí. Que uno de los bolsos del Carla tenía medicamentos y cosas, entonces si alguien lo tomó por error porque lo entregaron, hubo un error en la persona de hoy que recibió una la bolsa.
Ah, ok.
Entonces se confundió.
Está bien, pero prefiero que usted dé el anuncio, ¿está bien? Sí. Okay. We have a short announcement here.
Disculpen, para las personas que... I'm sorry. For the people that have that received your bags today for the accreditation, just one have a confusion. It's not the real bag that the staff give you. This guy, this
original, but this
yes.
bag in medication. Here, no?
Just was a confusion.
There's
Yes.
confusion in the
Was. Okay. Una bolsa se confundió, se entregó una bolsa personal hacia las personas que recibieron hoy la bolsa de Carla 2024. Entonces, si es que alguien la puede revisar dentro de sus bolsas y después se las podemos cambiar. Eso. Ah. Yes, check your bag, please. Yes.
En español, explícanos qué cosa tiene.
Esa.
Continuamos con un panel, por favor, para que no abandonen la sala y continúen con el Carla 2024. Okay, no problem. Thank you. Sí, no sé bien.
Hola Luis, soy
¿Cómo estás?
Nicolás. Yo
¿Cómo
te
estás, Nicolás?
presento brevemente y te corto.
Vale.
Session now we have a sponsored talk. It's a panel that will be led by Luis Diaz, and this panel will talk about power and efficiency, the new era of technology with Dell technologies, AMD and NVIDIA. There's one of each in the panel, so I pass the mic to Luis, and we have later on a coffee, so we will be sharp.
Thank you, Nico, and thank you to everyone. Good morning, buenos dias, bom dia to everybody, and welcome to the new era of technology with Dell, AMD, and NVIDIA. I'm Luis Diaz, Field Product Manager at Dell for AMD Business. I'm going to be your moderator for the next minutes. And today we will discuss about how these three companies are leading the technological transformation throughout solutions that can complement perfectly between power and efficiency in the same formula for HPC and artificial intelligence. Okay, for that I have the pleasure to be in the same stage with this distinguished panel. So let me introduce you to each of these rock stars. So let me start with Juan. Juan Moscoso is Data Center and Cloud Sales Manager for Spanish-spoken South America at AMD. He is well known here in Chile. So then we have Fabio Alves de Oliveira, Business Manager for Higher Education and Research at NVIDIA. And last but not least, we have Alexandre Ventura de Moraes, AMD Sales Specialist at Dell. Guys, welcome and thank you for having us today. Let's have a great discussion on HPC and artificial intelligence, okay? All right, Juan, what if we start with you? So I have this question on AMD. So it is the increasing demand for computing power in both CPUs and GPUs brings great challenges, as you may know, for HPC data centers. Considering that AMD has the most high-performance core processors, what is AMD doing on this matter?
Well, thank you very much, Luis, for that invitation. And AMD is very proud to be part of the top 500 list. And one of the most important things is AMD already has 156 supercomputer in the top of 500. And that's mean one of the three of supercomputing are using our technology. And as well, 60% of that technology is the more power efficiency in the market. So that's in place many things. Between them, I think it's the highlight is our technology processor lithography. Okay, and with that we are delivering more core counts, more technology with less power energy consumption. So that is the key for us, because AMD in each generation is offering more performance, breaking the paradigm of the more consuming, and that is a benefit directly to the end of customer.
Thank you, Juan. And this kind of performance, I mean, 192 cores in a single CPU, right? That's your next generation. So that's a huge number, right?
It's a secret. It's a secret to the October 10, but no joke. Yes. Now in our fourth generation, we have 128 cores per CPU, and the new generation brings to 182.
Cool. That's a huge number. And just to have a propaganda here, we are going to have this kind of CPUs, that's a gossip, in our next generation of PowerEdge servers, so stay tuned by the end of this year and the beginning of the next one, okay? So thank you, Juan. Thank you so much. Let me continue with you, Fabio. And how does NVIDIA, through its solutions currently available on the market, see the future of computing with that growing demand for resources?
That's a great question. Thank you again for the opportunity here. So we see HPCs being reinvented by the use of artificial intelligence, right? And we see like the modern supercomputing workloads, they need a high demand of compute because you have to do the processing at the data center, and sometimes you have to do the processing at the edge. So the ever-increasing data that is being created worldwide requires what everyone is calling so accelerated computing, right? So accelerated computing for us is also sustainable computing because the idea is to process things in a faster way and trying to consume less energy, right? So, but what NVIDIA is doing to achieve that is to not just to create the hardware itself, but support researchers and developers by providing tools or SDKs or frameworks that help them extract the maximum performance from a GPU. And we see for the modern supercomputers, it's not just the compute, but you have to have like a high performance interconnect. You have to have a high performance CPUs, and also all the software that help them, the researchers doing their work, extracting the maximum performance for these systems. That's our vision, right? So it's accelerated computing and sustainable computing being together.
Thank you, Fabio. And I believe that you described it very well. So let's say that HPC is the muscle that powers the brain of artificial intelligence, right?
Yeah, I saw once Matteo Valero mentioned, so there's no AI without HPC, right? So we only get there with HPC. So it takes a lot of time. It took a lot of time to get there, and this is what we see.
Awesome. Thank you, Fabio. And let's continue with you, Alex. So let me get you this question. How is Dell Technologies in collaboration with, of course, AMD and NVIDIA delivering cutting-edge infrastructure to meet the growing demand for HPC and AI? And what are those unique advantages on Dell PowerEdge server with AMD EPYC processors and NVIDIA GPUs in terms of performance, energy efficiency, and AI-driven workloads? Please.
Thanks, Luis. So Dell Technologies, in collaboration with AMD and NVIDIA, is truly the forefront innovations when it comes to AI and HPC. You know? And this combination delivered the best performance when you talk about the CPUs and GPUs. And this combination delivered this perfect performance with energy efficiency. You know? And make it perfect headline to most demand the HPC and AI today, because this is a huge demand. You know? And for example, Dell has a AI factory. You know, that the AI factory is a combination between the NVIDIA and AMD and other vendors, but the best vision with Dell and AI factory is that because we can help our customer to accelerate their projects with AI, because we have the big ecosystem with software, hardware, and solutions, and we have a big number of the use case for artificial intelligence in the world, that we can use that to help our customers to get the insight or to accelerate their process to implement the AI artificial intelligence. And we have some numbers that, for example, 76% of business leaders believe that the AI add value for their business. For 73% say that the data and the intellectual property is our true value for the third party may have the access, for this kind of research. And for Dell, the vision is that the cost is the major consideration when we talk about LLM inference on-prime. And then when we see the on-prime versus cloud or versus API, for instance, the Dell did a study that over the 3 years we have up to four times more cost efficient than public cloud, and 8 times more effective than token based in API.
Thank you, Alex. Thank you, Alex. Definitely at Dell, we are creating technologies that drive human progress with doubt. So let's get into the fourth question very quick. So that's for you, Alex, now that you got the microphone. In today's rapidly evolving landscape where HPC is essentially to drive innovation, how is Dell addressing that balance between expanding compute power and managing energy efficiency? Do you have any success case that you want to share?
Yeah. First of all, I research from Hyperon research about energy efficiency for data centers, where 57% respond that wanted to expand their data centers, but with lower energy consumptions. And then for 60% of response indicate that energy costs will delay their projects for HPC. And then a solution, 56% respond that their proper priority is an efficient energy management. So they need to have more configuration capabilities to be more efficient. And let me share with you how Dell, AMD, and NVIDIA have been addressed these challenges with advanced energy efficiency and solution that maximize performance for Senapad. So Senapad from São Paulo is the 9th national HPC centers from Brazil, and their mission is to support the research and development of computation science and providing high performance innovation and related services, acting as center of excellence in new computation trends and contribute to formation of the scientific and the business community. Senapad has now the cluster that the name is Ada Lovelace, that have 80,305 ROM cores and 69,115 CUDA cores, 36.4 terabyte for RAM, and 1.5 petaflop set storage. And then Ada Lovelace has 70 nodes with AMD EPYC ROM and NVIDIA Tesla A100, and deliver impressive 291 teraflops of CPUs and 97 teraflop GPUs interconnected by infinite band. The biggest contribution of Dell was to use our CSC, that our customer solution center in Austin, that have the many different cluster and configuration, and this helped the Senapad to see the best configuration between server, processors, GPUs, to make the great configuration for this cluster. And Senapad together with Dell can now provide a great resources for with NVIDIA and AMD, provide the great resources to researchers and to centers of researches.
Awesome. Thank you, Alex. And I believe that the time is over. With that, we close our Q&A cycle for the panelists. Thank you guys so much for your participation, and thank you for the audience for having us today. Don't forget to come by to our stand outside of the auditorium. Thank you so much and have a good one.
Thank you.
We want to thank you, the sponsors. Dell made it possible for us to be here. I mean, in money terms. So it's very important for us and for all the technology also. So the coffee is there. There is like gluten-free food for the people who needs it. Just ask for it there.
Hello from the children of planet Earth.
Hey, hey, okay. Ok, no sé, vamos a empezar. ¿Sí? Ahí está Carla, por lo menos entró Carla. No. Ginés vino, atrajo a la gente. Ahí arrastra, ahí arrastra. Hello, hello. Let's start with our next step in this conference, Carla conference. Hello, everybody. We are starting a new invited talk. We have here Alberto Ross from Universidad of Murcia. He's a full-time professor there in the computer science department. He got his PhD a lot of time ago when he was young and beauty, and this is the effect of doing research in computer architecture, you know. Well, let's start. We have a couple of minutes behind schedule, so let's do it. Thanks for coming, and the floor is yours.
Thanks a lot, Esteban, for the introduction. Buenos días, Santiago. Thanks also to Carla for inviting me to this talk. I'm very happy to be here and able to present a work that we have been doing recently. So its title is Accurate Predictions for High Performance Processors. We'll start with this graph. No? We are talking here about HPC. This is a graph that was taken in the Google data centers. Data centers, of course, are, as in the previous talk were said, there are many cores there, right? There are millions of cores. So, but there are millions of cores that they are not doing useful work all the time. Most of the time, actually, they are idle. But not just because there are nothing running there, but because the processor is stalled, just waiting for some dependencies, some data from memory, or other things. So Google did this study in their data centers and found out that only, I don't know if this, only 32% of the time the cores were doing useful work. For the rest of the time, they are stalled due to different reasons. This was running a Google search app. And now here we can see the three main reasons behind that. So first of all was the latency at the front end. So we need to fetch instructions because without instructions, we cannot execute them. Then the next part, the biggest one, was the backend memory. So this instruction work with data, and you need data. This is big problem too. And then, because we have out-of-order processors and they are very aggressive executing, they do sometimes bad speculation. Trying to do some work, but speculating on some value or some path the code will take, and it's not valid, it's not the current one, and we need to squash the full pipeline. So these are the three main causes here for loss of performance. So this is what I say in this talk is prediction is all you need. There is a famous paper called Attention is all you need, right? Very famous now for AI and enable of this ChatGPT and the current AI trends. So for the core performance, prediction is all you need. And actually you can cover all these phases with prediction mechanisms. So I will talk in this talk about 3 of the prediction mechanisms that we have been developing in the recent years. Each of them to target the 3 points here. So the first one is for front-end latency. So front-end latency, the problem in data centers is that the application's footprint, the amount of code that they have, is much more higher than what it fits in the L1 cache, in the small cache that hold the instructions. Right? And sometimes even in the L2, which is 1 megabyte. So this is one of the problems. You need all the instructions ready there, because if not, we cannot fill the pipeline. So our solution for that is an instruction prefetcher. So fetch the data before the processor will, or fetch the instructions before the processor will need it. And this was published at ISCA 21, and I will comment first on this one. Then, data. We need data, right? So data, the ideal is that it's in the L1 data cache, but most of the time it's not. You need to go to memory to fetch it. And this cache cause not only stalls because you don't have the data, but it also causes late detection of bad speculations. So in our code, sometimes we have a branch, and this branch depends on a load that missing cache and needs to go to memory. So if the branch is not predicted correctly, we will take a lot of time to recover from that. So prefetching is good for these 2% here. So our solution is a data prefetcher that we published in Macro 22, and this is the second thing that I will comment on. And finally, the last part of this graph is bad speculation, which the main 2 reasons for that is either branch prediction, or actually branch mispredictions, or memory dependent mispredictions. With this, I will talk a little bit at the end about memory dependent misprediction, what there are, but there are getting more and more critical, because there are more as the processor get more wide. And we present a paper this year in SPCA, and I will talk about it a little bit too. And about branch prediction, will for sure not have time to present that, so I will not include it in this talk. But we were recently in Buenos Aires with very nice hosts presenting this work. So I will start with the first 2 techniques that are about prefetching. So basically, we need to have both data and instructions ready very close to the processor, where the access latency could be as low as possible. Ideally, I want a huge memory that takes 1 cycle and I can read all the things, right? But this is not possible because of technology reasons. So what we have is a big memory, but you have a lot of cycles to access it. Of course, if the processor needs to access the memory all the time with 300 cycles, it will be very slow. So we have cache hierarchies, right? L1, L2, L3, smaller one, 4 or 5 cycles. And what we want is the data to be there. But still there are many misses, and we need prefetching. So prefetching is basically, I can find data, I know what the processor is going to ask for it, and I will move the data from memory or from L3 to a higher level, to a lower level, sorry, ideally to L1. So there are 2 questions to answer when we do prefetching, is which data the processor is going to ask, but also very importantly, when. And when is something that is not in all predictions, but is very typical for prefetching, and is key for the research that we do. So we call this when timeliness. We want the prefetch to be ready whenever we need it. So we have here a timeline, and this is latency that will take it, yeah. So this is a prefetch that we do. Will fill the cache with address A, and at some point the address A will be evicted from the cache. So this is the typical prefetch thing. Prefetch, put it in the cache, after some time, because you put many things, you put it out. Timely, what is timely? Timely is that you access exactly the data in this time, from when you put it in your cache until you take it out. You can have it late, that is, I bring my data and my processor asks for it before it came. It's not bad, it's good, but could be better. Or you can have it early. Like I put it in my cache, it went out, and I need to, and I lost the opportunity. And it can be wrong, which is not timely. I will never use it. There have been many prefetch championships over the years, and I will comment through them. Usually they are sponsored and promoted by companies like Intel, Google, and they are very nice contests because all the contestants go with the same rules. So you have your code, they test it, and the one that prefetch better, more accurate, is the one that usually win the contest. And there have been many. The first one was in 2009. You need to prefetch for the one data cache and for the L2. The second one, 2015, was only for the L2. There were the third one for all the levels. You could do your prefetcher in any level. And there was also an Insation prefetching championship very recently, and an ML, of course, prefetching championship too, for the L3. So it has a lot of movement, a lot of people participating in them, and advanced quite a lot of the state of the art. So, say that introduction, I will describe briefly the three papers and the three ideas that we have here. We will go into many implementation details, just the concept of them. So, as I mentioned, instruction prefetching is fundamental. We need good prefetchers. And we propose this entangling prefetcher that competed in the first instruction prefetching championship and was the winner of it, so the one that got more performance. And then in this paper we have a cost-effective version of it, like trying to reduce the kilobytes of storage to do prefetching. The concept that we have here. So let's say you have instruction L, and it will miss in the cache. You need to pay some latency to go to L2, L3 memory, and then fetch it. It's time that the processor is there without doing much. So what you need to do is to go back in time. If you could take a travel machine, you go back and say, at that point in time, I'm going to bring the line here. But wait a minute, how do I know what time is that one, right? So what we found out is that instruction is not executed in isolation. There are other instructions that are executing. So if we can take one instruction close to the time that we need to do our prefetch, that can serve as a reference point. This is basically what we do. We take here access B, is the previous access that happened before the time that is good to prefetch L. And I'm going to say access B gets entangled with access L. B is the source, L is the destination. Every time I see B in my code, I want L in my cache. That's the concept. We play a little bit to say, oh, I like the topic of quantum and entanglement, and that's why we put that name to this prefetcher. But this is very expensive. So we cannot store all the pairs for all the instruction in the code. So we need to compress the things. First, we move to cache lines. So I have here an example of how the instruction order in caches, in cache lines. So A is an instruction in a cache line. Then another cache line has B, C, and D. And then the E is a branch that jumps to L. This is a different, it's not consecutive, but that's why I changed the color here. So we call here a basic block, which is a running execution of code that didn't do any branch, any jump to another code. And basically what we do is to entangle the head of the basic blocks. So I know that every time I see the access of any instruction in this cache line, I'm going to bring this cache line to my cache. This is basically with what the prefetcher does. It does a little bit more. We take, when we see A, instruction A, we will bring the whole basic block to our cache. We will find the entangled line, and we will bring also the whole basic block of the entangled line. And with that, if there are more entangled, we bring more, and we can bring all things in our cache. So to summarize the results of this, we will see a little bit this graph. This is the kilobyte of storage that the prefetcher takes. This is the speed up that we get. And these 2 points is when you double and triple the size of your cache. So a lot of kilobytes, but not too much performance. This is an ideal L1 instruction cache. You can have other prefetchers, next line, RDIP, I will not discuss with them, Mana, others. And here on the top, the 3 winners of the championship, instruction prefetching championship. EP is the entangled prefetcher for instructions. And there is a lot of kilobyte of storage. So what we did in this work is to try to make more size-aware versions where we have quite good performance of almost 10% for only the size of the cache, basically 40 kilobytes. So this is the first of the works. The second moves to data prefetching. This is the work that I did with people, with colleagues from Zaragoza and from India. And basically, well, I would like to talk about this following the name of the prefetcher. The long name here is an L1D prefetcher. It's a timely local delta. I'm going to explain what it is, and it's very accurate. So we want it in L1D first. Why in the L1D? Because you have virtual addresses there. You have an instruction pointer. You can do cost-based prefetching. You can do many things there, and it's the shorter latency one. What we call delta. Delta, usually when you prefetch with strides. Stride is the difference between 2 consecutive accesses. I access address 12, address 15. So the difference is 3 cache lines, for example, 3 items. Delta is the difference with any of the previous cache lines that you access. And that gives you a lot of possibilities. For example, here to fetch address 15, I can do it with +8 from 7, or +5 from 10, or +3 from 12. Why is delta good? Well, you can have a stride that may be a little bit irregular, like +1, +3, +5. These follow +1, +3, +5, +1, +3, +5. But if I prefetch always with delta 9, I get all hits. Choose any, 13, +9, 22 is a hit. I prefetch an address that will be taken. Even if the processor is out of order, we find that we can find the delta that does not care about the reordering. And it needs to be local. Local means per instruction. Each instruction has a different delta. There are other works that do global, which is this base offset prefetcher, and this is an application MCF from a spec. And if you take global, you take delta 62, and you get only cover 2% of the access, of the misses. But if you take per different load, the best one, sometimes it's 64, sometimes it's 10, you can get up to 10%. This is an application that is very hard to prefetch. And finally, here this needs to be timely. So we have here the delta. This is +2, +2, +2. We can take delta 4, 6, 8, 10. Which one do we take? So we measure latency and say, okay, to prefetch 12, I need it from 2 because the latency that takes 12 is this one. So delta 10 will be good. So we learn all these deltas, and basically we have history table to put all the accesses and a delta table to learn all the deltas. It's very accurate because we measure for every search the recurrence of a delta, and when it gets 100% after some, we know that it will be very accurate. And we have a decision. Yes, the accuracy is higher than 65, we go to L1. If it's 35, we go to L2, we play with more, going to LLC, going to another levels. This is a good trade-off that we saw there. So it's very accurate and same graphs, same numbers. Well, some state-of-the-art prefetchers, and here is our prefetcher Bertie, which is also only 2.5 kilobytes, and it's 9% speed up, more or less, what you can get there. We did more work on this prefetcher. It's not only for L1D, it's contested in the ML prefetching, not being an ML prefetching technique, because I didn't use any ML here. It was able to win the championship over other ML prefetchers. So for my opinion on this is that for very simple problems like prefetching, that you know exactly what is the problem, sometimes heuristics work better than AI. For more intractable problems like language, images, and that, of course, AI is always beating it. And then in this micro this year, we will be presenting also a secure version, because security is also very important, and we'll be presenting a secure version on this prefetching. Prefetcher. The key thing here is that you can do everything when the instruction commit, not on the speculative path. And with that, what you get is that your training, your prefetching is never speculative, and you don't have problems with meltdown, Spectre attack that appeared a few years ago. So to finish with the presentation, I will do the third paper, which is was presented in HPC this year with my PhD student Sebastian. And then I will talk about memory independence prediction, because it's a topic that has not been working in many years, but is very, very interesting. So basically, it's fundamental for enable memory level parallelism. You have loads, we have stores, they need to be reordered because the processor will try to reorder, and we need to be sure that the execution is correct. So we propose FAST, which is from path-aware store distance, and is quite accurate in the sense that it reduces the misprediction of the state-of-the-art predictors by 62.5%. This in the end translates to very small performance improvements of a few percent, but it's in future cores it will be even larger. So we need to identify the single dependent store, and we need to learn the proper context information for them. I will explain a little bit what I mean here. But first of all, crash course on memory dependence prediction. So this is the order of the program. This is an old store. This is a younger load. They are executing like that. And this is a memory dependence. Both the store and the load access the same data. Obviously, the load needs to read the data that was written in the memory. If not, the program will not be correct. So how this is implemented in real systems? So the load, when execute, will snoop a queue of all the stores, and we'll see which one has the address resolved, which one have not. If you find the store with the address, you say, okay, I need the data from you. So give me the data. I will not go to memory because it's not valid, the one there. Mind that the store may be with the data computed, but not written to memory yet. And that's good. This is called store to load forwarding. But what happens if the processor decides that A should be load of A should be executed before a store of A? So for that, what we do is, I don't know. I execute, and if it's finally I go to memory to take this data, and if the data is not good because the store resolved later and is address A, the store will snoop all the queue of loads and say, wait a minute, this load took a data which is my data, I need to give it, and to give from memory, so it's wrong. I need to squash this pipeline. Clean, I need to restart. The execution takes a lot of time. So we need to predict that. So the first thing is, okay, is there a previous dependent store of me? This is why I need to do to squash. So if there is no dependent store, I can go and execute the load, If there is, I can wait until it resolves, and I will do this pair load store in order. If I miss the misprediction, but I got a wrong value, this is very bad, because I need to squash the pipeline. But if I wait, but I didn't need to wait, this is bad, but not so bad, because I lose a few cycles, but I don't need to squash the pipeline. So this problem is from the 90s, and was many papers about it. I say, what's not solved on those years? Yes, for the computers of those years. So even not in those years, we have Nehalen from 2008. And this is the misses per kilo instructions that they are getting. But as the processor gets more deep, more aggressive, the reordering happens more. And then the misses increases quite a lot. This is with all the predictor that we measure in our paper. But it's even worse, because the more increases the pipeline, a squash is more costly. So this is performance with respect to an ideal predictor, and it can get to 6% difference with some predictors and 4 or 2 with others. The important point is that will increase in the future processors. So we need to do 2 things. First, to precisely identify a single dependent store, and then to learn the context, the proper context information for that. So, single store. So the loads, our finding is that the loads depend on a single store, most of the time. There are exceptions, 0.0%. And these are narrow store, like a store to 1 byte to 1 byte, 1 byte, followed by the load that reads for 8 bytes. Okay? But this happen, 70% of these, the stores are executed in order. And there is no problem if you just take the dependence from the last one. Then we have another option that is the other, that is several stores that take the target the same address as the load. But only the one that is closer to the load is the one that will give the data. So it's good. So we just take one store. Next, we need to learn the context. This is very important from branch predictor. There has been a lot of work on that. So I have this load here, this store, and I have many branches in between. And I take the history of execution of the branches, and with that I predict if there is a dependence or not. Our main finding here is that previous, as in branch prediction, previous predictor do not know which history to take. Take 2, they move to 8, they try to find it dynamically. We say that the proper history is the difference, the number of branches that are between the load and the store. And this is only unique for memory dependence prediction. And with that you can save a lot of tracking of the information and shrink your predictor quite a lot. So we take conditional branches, all the branches that can change the path, we track them, if they are taken or taken, and if they are indirect, to where they jump, and with that we form our predictor. So I will skip this one. I will go to the result of MPKI that says we reduce, this is our bar here, this is the very bad misprediction, this is the not so very bad misprediction, and we get a huge reduction with the state of the art. And in performance, again, the same graph that I was showing before, kilobytes of storage, normalized execution time, and we go to our solution that is for different sizes, outperforming the previous ones. This is with respect to an ideal one. So, as a conclude, final remarks. So we need accurate predictors for high-performance computers. This is fundamental to improve performance. We can use prefetching both for instructions and for data. Ideally, we should prefetch to L1 because it's the shorter latency. And for memory dependence prediction, the key is to use exactly the history that is between the load and the store. So thanks a lot. And if you have questions, please, I will be happy to attend. Oh, well, thank you very much for your presentation. It was very interesting. We have time for a couple of questions. Anyone? No? I have plenty of questions. Okay. I'm gonna ask you only some. How is you show in the last slides, how do you evaluate your strategy in general? What kind of tools and strategy you use for evaluate your proposals?
Thank you. So there are many simulators, right? We need to use simulation because we're gonna tweak real systems. I would also like to mention, now that you had this question, that we are also trying to develop these things in a real core, RISC-V cores. We are into that, working with Barcelona Supercomputing Center and people there, and with other companies. But for this previous study, before going into the chip, we do simulators. There are many. For the prefetching, we have been using JAMSIM, basically because it's the one used for this prefetching championship, was built for that. And it's very useful because we have a lot of prefetchers that have been proposed there, tuned for that one, so you know that this is the best effort of the authors to do them. And for the latest work, we use our internal simulator in the group that we have been developing for years, because we didn't find that it's very well modeled in other simulators, and we wanted to model very accurately.
And the data? What data do you use? What application? And the size of the data you use?
So it depends a lot of the work, right? For the first work in insertion prefetcher, we took some traces that were collected by Qualcomm on server workloads, on their servers, so they are very useful. For data prefetching, we use spec mostly, but we also present the evaluation with graph parallel applications. And spec is always an option for memory dependent prediction.
Well, I have one more question, only one. And in your perspective, you are focusing on a single thread application performance, and in the last talk we saw Bernd talking about this craziness of a hierarchy, about the CPU, multiple core, multiple nodes. How, in your view, you need to focus on that size for the programmer? You have to be aware of the cache. You have to program focuses on cache, because if you don't use cache well, your application will suck. But at the end, we have this craziness of hierarchy. What is your advice for the young people having to learn? They have to learn more about the lower level, or they have to be happy with low performance in Python or C without caring about their code?
Thank you. So it's very important for the performance. Performance is always important, but nowadays we have libraries that are very, very high tuned. So I mean, depending on what you are working on, you don't need to learn exactly how they work. You can just use it, or if you are interested in what they do, it's a fun part, right? To go how this algorithm is made so fast in this system. And for the parallel work, I mean, I'm doing this work on microarchitecture very recently. My background is more on the parallelism. We have also a few papers this year on that. And yes, that's important. I mean, the parallel world is, you cannot, you need to parallelize to get the maximum of your performance. And then if you are stuck for some waiting time, as in the first speaker was saying, you are killing or your performance. So it's also a very interesting topic.
And I have the last one. Only the last. Well, thank you very much, Alberto.
Thank you. Thanks a lot, Esteban.
Sí, sí, claro, lógico.
For continuing with us, next presentation will be in Spanish by our diamond sponsor, Intel. Le voy a presentar a Santiago Cardona, que es el director de Latinoamérica para los países de habla hispana de Intel, y al doctor José Loiber, que es el director de infraestructura del Servicio Meteorológico Nacional de Computación en Argentina. Así que muchas gracias y les dejo el uso de la palabra a ustedes.
Hola, sí. Hola, muy buenas tardes ya, tardes. Un gusto estar aquí con ustedes. Gracias. Me presento, soy Santiago Cardona, director para Hispanoamérica de Intel. Es un placer para mí estar aquí, bueno, en una comunidad aquí tenemos un poco de todo, tenemos creo que, pues por supuesto, estudiantes, comunidad científica, muchas personas, bueno, presentes de toda América Latina y de otras partes del mundo, pues que están, por supuesto, metidas en el mundo del High Performance Computing. Entonces, bueno, me acompaña aquí Pablo Loiber, licenciado y director nacional de infraestructura tecnológica para el Servicio Meteorológico Nacional Argentino. Y entre Pablo y yo, pues queremos hablarles un poco de un caso de éxito que tenemos en conjunto en Argentina, con un HPC potenciado por Intel, con Intel Inside, que bueno, Pablo va a hablar bastante de ello y bueno, lo que hemos hecho juntos y bueno, que creo que va a ser de mucho interés para todos ustedes. Y antes de comenzar, me gustaría comenzar un poco hablando, antes de cederle la palabra a Pablo y tener este diálogo, sobre el Intel y sobre el rol de Intel en el mundo de High Performance Computing. Y para comenzar con esto, me gustaría remitirme a algo que es un poco más, todavía no vamos a entrar en el mundo de HPC, sino un poco más de alto nivel. Intel tiene una visión, un propósito muy, digamos, ambicioso. Nuestro propósito supremamente ambicioso es crear tecnología que cambie el mundo y que enriquezca la vida de todas las personas en la Tierra. Y cuando digo todas, son absolutamente todas las personas en la Tierra, es a lo que aspira Intel. Y siendo las 12:30 casi aquí en Santiago de Chile, me atrevería a decir que hoy todos los que estamos aquí presentes, existe 90% de probabilidad de que en algún momento de lo que hayan hecho hasta este momento en su vida, hayan hecho algo que tenga que ver con Intel. Porque el 90% de las infraestructuras de Internet corren sobre Intel. Entonces, en algún momento, si alguien utilizó una aplicación para pedir un servicio de transporte para venir aquí a la universidad, o si se metieron a una página a comprar algo, o pidieron algún servicio de un asistente de voz, muchísimas cosas que seguramente hicieron durante todo el día o usaron su computadora, seguramente ya pasó por algún componente de Intel. Entonces, es por eso que nosotros tenemos este propósito, ¿no? Que pues al final del día con nuestras tecnologías podamos enriquecer la vida de todas las personas en la Tierra y este maravilloso estilo de vida que tenemos hoy por hoy, potenciado por la tecnología y que nos facilita tantas cosas, pues bueno, en buena medida está potenciada por tecnologías de Intel que bueno, no llegan a ser tan profundas como de lo que vamos a hablar, que es el High Performance Computing, pero bueno, eso es un poco a lo que aspira Intel. Y para ejemplificar un poco esto, que bueno, aquí me encanta que estemos con una audiencia técnica y una audiencia tan geek, me atrevería a decir, es que en los últimos 50 años, gracias a las tecnologías de cómputo y particularmente de procesamiento, podemos afirmar que hemos tenido un crecimiento exponencial de capacidad de cómputo, que a su vez ha generado un progreso exponencial de todas nuestras capacidades como raza humana. Y para eso, digamos, una buena manera que se ilustra es con esas dos fotos que están ahí, en donde abajo hay una de lo que era una computadora, pues no me atrevería a llamarla supercomputadora ni mucho menos, pero una computadora de la época que bueno, audiencia geek, seguramente ustedes han oído hablar de una computadora de la época como el ENIAC. Esta foto no es el ENIAC, pero bueno, se parece bastante a lo que eran ese tipo de computadoras hace 50 años. Y hoy en día, ahí hay una persona que tiene una laptop, una computadora, una notebook, pero pues en la palma de nuestras manos tenemos el poder de cómputo brutal que pues podemos hacer de todo tipo de cosas solamente con lo que tenemos en la palma de la mano, y eso es justamente potenciado por este progreso que ha detonado la capacidad de cómputo que tenemos desde el primer microprocesador inventado, el Intel 4004, a donde hemos llegado hoy, donde pues de las cosas que hemos hablado, vamos a hablar aquí con Pablo de lo que potencian los procesadores Intel Xeon. Pues hemos llegado bastante lejos, y eso pues al final del día genera otro tipo de progreso, de desarrollo de la raza humana, de tener esa capacidad de cómputo para resolver los problemas más difíciles que tiene la humanidad, o pues hacer cosas como predecir el clima, entre muchas otras cosas, pues está potenciado justamente por eso. Y específicamente hablando de HPC y lo que hacemos nosotros como Intel para HPC, tenemos una propuesta de valor en la cual pues hay 5, digamos, diferentes aspectos de los cuales podemos hablar, pero en los que yo quisiera hacer énfasis en particular es en el ecosistema abierto. Intel, desde sus orígenes como empresa, y ahorita hablé de un procesador que, bueno, como estoy frente a una audiencia geek, me voy a permitir ser un poco más geek y hablar de, no sé, el Intel 4004, que fue el primer microprocesador inventado, que fue un procesador para calculadoras, pero luego de eso vinieron otros más, que fueron el de las primeras computadoras personales. Fueron justamente las primeras computadoras que vinieron a imponer un ecosistema abierto, que no fuera todo cerrado, que solamente esta caja para mí solo funciona con este código. No, Intel siempre se ha caracterizado desde sus inicios por promover un ecosistema abierto, y es uno de los grandes diferenciales pues que nos mantiene en el negocio por más de 50 años, y ese ecosistema abierto aplica para el software de los aceleradores, que son, digamos, una de las características más importantes que tienen los microprocesadores Intel Xeon, que dependiendo de la carga de trabajo tienen ciertos aceleradores que se pueden utilizar, y para eso tenemos un ecosistema abierto de software y de hardware. Entonces tenemos las dos. Y hablando de software, para que se hagan una idea, Intel es una empresa de alrededor de 110,000 empleados a nivel mundial. De esos 110,000, más de 15,000 son ingenieros de software. O sea, más del 10% de la planta de Intel, es casi 15% casi, son dedicados a software. Si tomáramos estos ingenieros que hacen software en Intel y creáramos una empresa aparte, que los sacamos a los 15,000 y creáramos una empresa aparte, Intel sería una de las 10 empresas más grandes de software del mundo. Y la razón por la cual tenemos toda esta cantidad de ingenieros dedicados a software es justamente por esta visión del ecosistema abierto, de que todo funcione, de estar todo probado y funcionando en conjunto, no solamente el hardware, el software, asegurar que esto funcione muy bien, que sea un ecosistema abierto, darle la facilidad a, en este caso, usuarios como ustedes para poder seleccionar la tecnología adecuada para el trabajo, para lo que necesiten hacer, y al final del día hacerle la vida fácil a desarrolladores o científicos como ustedes para traer nuevas ideas o al mercado o a la comunidad investigadora, como muchos de los que están aquí. Entonces, si se pueden quedar con una sola palabra, digamos, de todo esto, que de la propuesta de valor de Intel para HPC o dos palabras, es un ecosistema abierto. Eso es de la propuesta de valor más importante. Y creo yo que, bueno, ya haciendo transición aquí a Pablo, una de las razones por las cuales justamente el Servicio Meteorológico Nacional Argentino decidió tener Intel Inside en su supercomputadora Clementina 21, de la cual vamos a hablar, que es una supercomputadora que, bueno, el top 500 que todos ustedes conocen aquí está en el lugar 224, hoy día, sí, arrancó en 196, ahora está en 224, entonces
Estamos trabajando ahora junto con ustedes para a ver si podemos mejorar un poquito.
Con parte de esos 15.000 ingenieros de software que tenemos para hacer la optimización. Entonces, pues bueno, justamente Pablo, que como ya lo presenté, bueno, voy a dejar que él también se presente y hable, viene como director de infraestructura del Servicio Meteorológico Argentino, que bueno, tiene, aparte de esta supercomputadora que está dedicada para el clima, es una computadora que también está abierta justamente para el uso de diferentes usos científicos en la Argentina. Así que un placer, Pablo, estar aquí contigo. Y bueno, vamos a conversar un poco sobre esto. Y yo quisiera arrancar haciéndote una primera pregunta respecto a todo esto que aquí las tengo anotadas. Y la primera, por supuesto, es... Hablando del clima y bueno, el propósito primario que tiene Clementina 21 es cómo contribuye la tecnología de HPC justamente para mejorar la precisión pues, y toda la mejora de la predicción del clima.
Sí, bueno, buenas tardes, ¿cómo les va? Yo soy Pablo Loiber, soy, como dicen, el director de Infraestructura Tecnológica y de Datos del Servicio Meteorológico. Tengo dos sombreros en el servicio, uno meteorológico y otro que es mi métier, que es tecnológico. Y estoy en el Servicio Meteorológico, que está cumpliendo 152 años este viernes 4, de los cuales en los últimos 20 años el Servicio Meteorológico viene trabajando con modelado numérico para el pronóstico de la atmósfera, digamos, para pronóstico meteorológico, digamos. La incorporación de equipos de HPC, digamos, por supuesto, benefician significativamente la forma y los tiempos para llevar adelante los cálculos que tiene un modelo numérico de estas características, digamos. Nosotros decimos que hay un circuito virtuoso entre la incorporación de nuevas tecnologías, la investigación y la generación de un pronóstico. En particular, en la incorporación, las últimas incorporaciones de los equipos de HPC, porque teníamos un viejo equipo Silicon Graphic con el que se empezó a hacer el pronóstico, hasta que luego pasamos en 2015 a un equipo con procesadores Intel que se llama Guairamuyo, que es el encargado de hacer el pronóstico operativo del servicio meteorológico. Y el principal hito que logramos fue pasar de un pronóstico determinístico a un pronóstico por ensambles. ¿Esto qué significa? Es pasar de un pronóstico de una corrida a uno de muchas corridas que se llaman cada una de estas miembros para poder de todas las corridas hacer una estadística de ocurrencia de los eventos severos, ¿no? Entonces poder pronosticar con más información, con más datos, digamos, un porcentaje de ocurrencia de los eventos, más allá de que pasamos de una grilla de cálculo que estaba en unos 15 kilómetros a una grilla de 4 kilómetros para todo el servicio meteorológico. Eso es el grafito que está a la izquierda de ustedes, es la región sobre la que se calcula el pronóstico, digamos, así que incluye todo Chile, digamos. Esto ahí tenemos que mejorar cómo compartir la información. Acá tenemos una presentación, digamos, de la situación del equipo operativo. En el servicio meteorológico tenemos dos clústeres de supercómputo, digamos, en funcionamiento. El operativo, que se llama Guairamuyo, y Clementina, que es el para investigación.
Muy bien, Pablo. Y bueno, entendiendo justamente todo lo que tienes armado, y ahora hablábamos del ranking, en el top 500 está en 224. Y pues una de las cosas con las cuales hemos trabajado en conjunto es que, bueno, todavía esto no está a su máxima, digamos, capacidad, claro, ¿no? Entonces, ¿podrías contarnos un poco más sobre el proyecto de Clementina 21 y cuáles son las expectativas cuando esté a su máxima capacidad? ¿Qué podemos esperar?
Bueno, Clementina, digamos, es un proyecto muy ambicioso que el Servicio Meteorológico Argentino, digamos, se fue beneficiado, digamos, un poco por la experiencia que teníamos en la administración de equipos de estas características, para instalar este equipo que está destinado a la comunidad científica. No es un equipo operativo como Guairamuyo. Clementina es un equipo que va a estar destinado para la investigación, para definir las características y cómo queríamos que el equipo sea. se hizo todo un relevamiento de las necesidades de la comunidad científica, digamos. Eso está apalancado en un proyecto estratégico del gobierno, que es un proyecto el proyecto estratégico justamente para computación de alto desempeño y el Sistema Nacional de Supercómputo, del cual el Servicio Meteorológico se constituye en uno de los nodos, ¿no? Hay por supuesto, en diferentes universidades, de las cuales hay gente presente aquí, que tienen otros clústeres de supercómputo y formarían parte de la red. La idea es que el equipo esté destinado el 90% del tiempo a la comunidad científica y el Servicio Meteorológico se reserva un 10% de las horas de cómputo para sus propias investigaciones que tienen que ver con cómo evolucionan los softwares de modelado numérico para tomar beneficio de las nuevas tecnologías como son las aceleradoras. Porque, digamos, Guairamuyu no tiene aceleradores, tiene solo procesadores y pensamos que, digamos, la próxima generación vamos a necesitar aceleradores. Hoy por hoy, en lo que es el pronóstico operativo, porque la principal diferencia de Guaira con Clementina es que Guaira es operativa, digamos. Hay una obligación de un servicio público que tiene que estar funcionando 7x24, etcétera. Entonces, al día de hoy, con la última información que tengo, no hay ningún servicio meteorológico en el mundo que use sus sistemas de modelado numérico que aprovechen aceleradoras. O sea, está todo en investigación. Entonces, nosotros con Clementina nos posicionamos con una máquina in-house para hacer investigación, lo cual es fundamental.
Bueno, y qué bueno que estén pudiendo aprovechar y probablemente efectivamente la única que esté aprovechando toda esta capacidad de aceleradores para predicción del clima. Y justamente, bueno, ahora has hablado de aceleradores varias veces, pero en ese proceso de licitación, o sea, cuando el Servicio Meteorológico Argentino decide vamos a hacer una inversión en un HPC, ¿qué variables tecnológicas tuvieron en cuenta para tomar la decisión que al final los llevó a decidirse por Intel?
Nosotros teníamos la experiencia ya de haber, en realidad cuando hoy comenté la secuencia, entre el equipo de Silicon Graphics y Guairamuyu hubo en el medio un equipo más chiquito que lo armamos nosotros, o sea, compramos las partes y lo armamos. Y estuvo funcionando varios años con el pronóstico determinístico, digamos, el que corre una sola vez. Tuvimos un montón de variables a tener en cuenta, digamos. Básicamente, o sea, nosotros tuvimos como algo muy pesado el hecho del servicio que hay que prestar, digamos, de que hay un SLA, digamos, que si bien somos un servicio público, es un organismo del Estado, no es estrictamente a cumplirse, pero bueno, hay un compromiso de que el SLA sea muy pequeño, o sea, de que el equipo tenga que tener detrás, digamos, todo es basado en estándares y en sistemas con calidad comprobada y bueno, digamos, sacamos una licitación internacional muy estricta en la que pudieron participar solamente los fabricantes y bueno, eso, digamos, en ese sentido con Intel estamos muy satisfechos, digamos, porque sabemos que vamos a tener respuesta y vamos a tener soporte.
Soporte, acompañamiento.
Claro.
Entonces, bueno, lo cual nos orgullece muchísimo porque recuerdo yo casualmente cuando se hicieron las primeras pruebas de la puesta a punto, pues estaban ustedes allá, estaban ingenieros de nuestro lado, yo estaba, pude ver y bueno, pude presenciar que son procesos supremamente complejos de la puesta a punto y
porque
es fácil.
Para poder aplicar al top 500 se nos cerraba la ventana, se nos terminaba la ventana de aplicación, eso fue recuerdo en octubre, 27 de octubre.
Me acuerdo que fue un viernes en la tarde.
Así que fue un viernes que estiramos la medianoche hasta las 3 de la mañana por la cuestión de usos horarios y estuvimos así corriendo el benchmark para el top 500. Ahora, de hecho, bueno, estamos trabajando justamente codo a codo con Intel para volver a correrlo. Y yo, digamos, digo esto siempre que en el rol que me toca estar me pierdo la parte divertida, que es justamente estar hands-on en este tipo de desafíos, digamos, porque estamos ahora tratando de optimizar, junto con el apoyo de los profesionales de Intel, el equipo, la configuración óptima para poder sacarle el mayor jugo posible, digamos.
Sí, sí. Que creo que bueno, al final del día nosotros también pues queremos que ahí hay una muy buena foto de Clementina, pues que ese poder de cómputo que tiene pues se dé al 100% para que bueno, pues justamente contribuya ahí. Y pues bueno, creo que por lo que tus palabras, pues bueno, es parte del digamos del diferencial de Intel ha sido justo ese acompañamiento que en el cual, bueno, no sé si tienes algo más que quisieras compartir respecto a esta alianza que hemos tenido de trabajo
Claro,
conjunto.
digamos, o sea, nosotros, otras de las variables, digamos, que se tuvo en cuenta y bueno, y también otras que no se pueden soslayar, que tienen que ver con la comunidad, el uso y, digamos, el uso de estándares. Nosotros, desde el Servicio Meteorológico, en cuanto a lo que es HPC, tratamos de apoyar todo lo que tenga que ver con estándares para poder tener justamente más sostenibilidad en el tiempo. En ese sentido, bueno, los compiladores Intel eran, digamos, nada, casi como un commodity, digamos.
Sí, ¿no? Sí. Que bueno, por eso es que tenemos 15.000 ingenieros de software que están trabajando justamente en todas estas plataformas, incluyendo los compiladores, bueno, justamente para ponerlo al servicio de proyectos como Clementina 21. Y bueno, creo que algo más que quisieras, con lo que quisieras cerrar, Pablo.
No, nada, digamos, yo me siento muy orgulloso de poder haber llevado adelante este proyecto, digamos, espero que, digamos, poder servir a que la comunidad científica argentina y bueno y latinoamericana se beneficie de este tipo de infraestructura, así que bueno, nada, ojalá que todo salga bien y que nada, le podamos tener digamos un uptime llegando al 100% en el año.
Sí, y bueno, y de nuestro lado, pues en la siguiente corrida para el Top 500, bueno, vamos a trabajar mucho pues en conjunto para que Clementina siga escalando y de nuestro lado, pues estar en el Top 500 siempre, pues cualquier máquina es un gran desafío a nivel mundial. Sí. Que tengamos máquinas de Latinoamérica, en el Top 500 para Intel es un motivo también de orgullo porque pues no es algo sencillo ni por el poder de cómputo ni por la puesta a punto, así que bueno, a nosotros como Intel por supuesto que nos llena muchísimo de orgullo que un proyecto latinoamericano, específicamente pues aquí y gracias Pablo por estar aquí, de Argentina, pues esté en el Top 500, pues es muestra de lo que se puede hacer juntos en América Latina.
Muchas gracias.
Gracias.